Hi ladies, welcome to your snow day. Today we're going to be talking about binomial random variables. Okay ladies, let's review a little bit about what we did the other day because that certainly couldn't hurt. So when we're talking about adding two random variables together, that would be taking our total and saying that our total is x plus y. So our expected outcome of x is going to be our mean of x plus our mean of y. And that would be how we come up with our mean of our total, right? So that's how we do the mean. If we need to calculate variance or standard deviation, remember that we can only calculate variance first. Now, in order for that to happen, x and y have to be independent, and our total has to equal x plus y. If that's the case, then we can go ahead and calculate variance. So our variance for our total is going to be our variance for x plus our variance for y. And remember, again, that is squared. So if I need to get the standard deviation, I would take the square root of that. Okay, if I'm going to try to find the difference, that would be d equals x minus y. Then I need, in order to find my expected outcome for my difference, it's going to be, which essentially is the mean of the difference. That's going to be my mean of x minus my mean of y. Okay, same deal as before. If x and y are independent, then I can calculate my variance. But remember, even though it's a difference, this variance is still added. Why? Because I still have two sets of data. My variance in my data is increasing because I have two sets of data. So I still have to add the variance together. I know, it's strange, but there it is. Okay, ladies, so today we're going to talk about binomials. So let me give you three examples of what I mean when I say binomial, or a random variable that can be considered a binomial. So the first example is tossing a coin 5 times and counting the number of heads. Or the second example, spinning a roulette wheel 8 times and recording the number of times that it ends up being red or falls in the red slot. And the third, I could take a random sample of 100 babies and count the numbers of babies that are female. In all three of these examples, there were repeated trials of a chance process. The number of trials was fixed in advance, meaning that I knew how many trials I was going to start off with from the beginning, and each of the trials were independent, meaning that one did not affect the outcome of the other. So we'll call the outcomes in this case successes. That's kind of a new term, and the probability has to be the same for all the successes. So when I define a binomial setting, or when a random variable is binomial, that would be when we perform several independent trials of the same chance process and record the number of times that a particular outcome occurs. And that's essentially what we're going to be doing. Now, in order for something to be binomial, there are 4 conditions that must occur. The first, well, we'll get to the first. The way we remember them is with the letters BINS, B-I-N-S. So the first one, B, stands for binary. And binary means just straight up either or, right? So I either have a success, woohoo, and I feel like there's 2 C's, or I have a failure. So in the example of kids and counting females of the babies that were born, we would say being born female would be a success, and then being born male would be failure in that particular case. Then if we were to do an example with the roulette wheel, there's actually 3 options on a roulette wheel. You can have red or green or black. So a success would have been red and a failure would have been green or black. So there can actually be more than 2 possibilities. The possibilities just have to fall in success or failure. Okay, the I stands for independent, meaning that every single trial is independent. Knowing one outcome has no effect on the next trial. Okay, the N stands for number, and it's really number of trials. So you need to have a set fixed number of trials that you begin with, and that's key. If you don't have that, it's not a binomial. It's something else that we'll learn later next week. And then we have successes. Okay, so S stands for success. So the probability for success, probability of each success has to be the same. Oops. And we write that the same way we've done before, probability of each outcome. One thing that can trip people up is sometimes you'll have a problem that looks like binomial, but it's going to ask you to count the successes. So we need to make sure that we know how many trials we're doing to begin with. This is a key point, and I'll distinguish this as we're going along. So big summary, we want to make sure that we have success or failure. They're all independent. We have a set number of trials, and the probability is the same for each success. So they're all identical probabilities because they're in and as well as independent. So make sure that we're counting successes, not counting trials. Okay, so let's do some definitions here. So just to sum up, a binomial random variable. That's going to be a discrete random variable associated with a binomial setting. So kind of the same thing we've been talking about before, random variables, but now we're talking about random variables that are in fact in a binomial setting. So of course they have binomial distributions. This would be the probability distribution associated with a binomial random variable. So the same thing we've been doing before, looking at those tables of distribution. Now there are some variables that we use that are specific to binomials. N is our number of trials, and P is our probability of success for each trial. And these are going to be important. So basically, this is the same thing we've been doing before, but now it's a specific case of us having binomials. Okay, so let's look at some 5 specific examples and try to determine whether the random variables below have a binomial distribution. And we're going to justify our answer a bit by doing bins for each one. So the first one, roll a fair die 10 times and let x equal the number of 6s. Okay, is it binary? That's our first question. Oh yes, our successes are 6 and our failure is anything that's not a 6. Is it independent? Yep, knowing the past rolls doesn't give us more information about the outcome of the future. Do we have a set number of trials? Yes, we said we were going to roll it 10 times, so we're good there. Success, yes, the probability of success is always 1/6. So this is a binomial setting, woohoo! X is the binomial, the n would be 10, and the p would be 1/6. So that's just to show you for that specific one, n equals 10 and p equals 1/6. Okay, this next one. You're going to shoot a basketball 20 times from various distances on the court. Let y equal the number of shots made. Okay, is it binary? Yes, because we either success equals making a shot, failure is missing a shot. Are they independent? Yeah. Evidence suggests, and it's very difficult to explain this, but essentially evidence suggests that it's reasonable to assume that making a shot doesn't change the probability of making the next shot, aka there is no law of averages. Okay, so is there a number? Yes, there are 20 trials. Awesome. Okay, success? No. In this case, the probability changes when we change from different distances of the gym, right? So this is not binomial. Goodbye this example. Okay, third one. Observe the next 100 cars that go by and let C equal color. So binary. Is it one thing or another? Is there a success or failure? No. Lots of colors. So that one's a no. Okay, fourth example. I'm going to shuffle a deck of cards, turn over the top card, then put the card back in the deck and shuffle again. I'm going to repeat this 10 times and let x equal the number of aces that I observe. Okay, so binary. Yes, success is getting an ace, failure is not getting an ace. Okay, is it independent? Actually, in this case, it is because we have replacement. We're putting the card back into the deck each time, so our first choice won't affect the rest. Do we have a set number of trials? Yes, we have 10 trials, so we're good there. And then success. Well, the probability of success would be, let's see, there's 4 aces in a deck out of 52 cards, so 4 divided by 54 for each trial. So this is a binomial setting in this particular example. And n would be our number of trials, that would be 10, and our probability of success in getting an ace, because there are 4 aces in a deck, is 4 divided by 52. Okay, this last one, flip a coin. If it's heads, roll a 6-sided die. If it's tails, roll an 8-sided die. Repeat this process 5 times. Let W equal the number of 5s you roll. Okay, so binary, sure. Success is 5, failure is not 5. Independent, one roll doesn't affect the next one. A dice has no memory, so that's true. Number of trials, yep, we have 5 in advance. Success, no, probability is going to change on whether or not we roll a 6-sided die or an 8-sided die, so this is not a binomial setting. Goodbye, this one. Okay, let's start with an example. In many games involving dice, rolling doubles is desirable. Rolling doubles means that the outcomes of 2 dice are the same, such as 1 and 1 or 5 and 5. The probability of rolling doubles when rolling dice is 6 out of 36 or 1/6. So we're going to set x to equal the number of doubles in 4 rolls of 2 dice. Okay, is this a binomial distribution? Well, let's go through our bins. So is it binary? Yep, I can either have doubles as a success or failure as no doubles. Is it independent? Sure, one roll won't affect the next outcome, so it's independent. Do I have the set number of trials? I believe it says 4 rolls, so we're good there. And success, is each probability the same? It is, because in each case it's 1/6. So that's going to be n equals 4 and p equals 1/6. Okay, so it's asking, what is the probability that x equals 0? Well, what does it mean by that? What it means by that when it says x equals 0 is that, in fact, there are no doubles. So 4 rolls, all are not doubles. Since we know the probability of getting doubles is 1/6, we have to use our complement rule and say, okay, well, 1 minus 1/6 is 5/6. So our probability of not getting doubles is 5/6. So I'm going to write this out here. We have the probability of x equals 0. In this particular case, another way to write that is the probability of me getting a failure, a failure, a failure, and a failure. Okay, so essentially what I'm going to be doing is multiplying 5/6 times 5/6 times 5/6 times 5/6. So that's the probability of getting a failure every single time. Easier way to write that would be the probability of 5/6 to the 4th power. If I do that on my calculator, I find that that's 0.482. So the probability that I won't get doubles is essentially 48%. Okay, ladies, so I put this next one on the next page because it's going to take a little bit of doing. So there's 4 different ways to roll doubles once in 4 tries. I could have a success, and then I could have 3 failures, or I could have a failure, a success, and 2 failures, or I could have a failure, a success, and a failure, or I could have failure, 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 and success in terms of doubles. So those are the options that I can have for doubles in 4 tries. Doubles once, because this is saying x equals 1, I want doubles once in these 4. Okay, so because the tries are independent, the multiplication rule for independent events applies. So let's take a look at each of these probabilities. So the probability for our first situation, success is 1/6, and then we have 3 failures, right? So this would be our probability for our first try there, with success being the first one. And I can sort of simplify this a bit and say it's 5/6 to the third, right? Okay, let's look at our next probability. Probability of failure, success, failure, failure. Well, probability of failure is 5/6. Then I have a success, 1/6. And then I have a failure of 5/6 and then a failure of 5/6. And if I could rewrite that, which I can, it's 1/6 again times 5/6 to the third. That's supposed to be 3. There we go. Okay, let's try the next one. Probability of failure, failure, success, failure is going to be 5/6 times 5/6 times 1/6 times 5/6. So you'll see again, it's 1/6, 5/6 to the third. And if I do the fourth one, you're going to find that it's the exact same thing. Okay, so here's the next one. Ooh, it's a pattern. Okay, 5/6, 5/6, 5/6, 1/6. Same deal. So as I'm looking at these, the probabilities for each of these is identical. Here's the probability for my first, the second, the third, and the fourth. So an easier way for me to write this is the probability of 1 minus x is essentially, let's see, there were 4 possibilities of arrangements, so 4 times the probability of each one. That was 1/6 times 5/6 to the third. So 4 different arrangements having 1 success and 3 failures. If I do the math, I find out that this is 0.386. What if I was mean and I made you do this again, only I wanted to find the probability of x equals 2. So having 2 successes. So 2 doubles in 4 rolls. Let's come up again with the combinations I could have. So I could have success, success, failure, failure. Or I could have failure, failure, success, success. Or I could have failure, success, failure, success. Or I could have failure, success, success, failure. Or success, failure, success, failure. Or success, failure, failure, success. Okay, so there's 6 different combinations. Well, let's use the pattern that we used before. We know that 2 of these are going to be successes and 4 are going to be failures. And we know that there's 6 different combinations. So, without doing all this crazy math up there, I'm just going to say the probability of x equals 2, since there's 6 different possible ways we can do this. And the probability of winning is 1/6, and I'm going to have 2 wins. And the probability of failure is 5/6, and I'm going to have 2 of those. This is my equation, 0.116. Okay, so the pattern for this works every single time. So the pattern is the probability of k being, or x being equal to k, where k is successes, so k is successes in n trials. Then this is equal to my number of arrangements times the probability of my number of successes times my 1 minus my probability of success, so my probability of failure, n minus k. So when you look at this, this is my probability of success and the number of times that I have success. This is my probability of failure and the number of times that I have failure. My total number of trials minus my number of successes. Okay, so our new problem becomes, how do we find our number of arrangements of successes? So there's a really nice way to do this. And I'm going to give you the formula first, and then I'm going to explain it to you. So essentially, the way we write this, here's the formula. It's called the binomial coefficient. And the binomial coefficient represents how we get our number of arrangements of successes. So the number of ways of arranging k successes in, or among is probably a better word, n observations. So the easiest way to read this little notation is you kind of read this one as n choose k. So with the example I just gave you, we essentially had 4 trials, and we were picking 2 successes out of those trials. So we take our number of trials and we do a factorial, and then we divide that by our number of successes, which we're going to make 2 factorial, and then n minus k, which in this case is also 2 factorial. So just to refresh, because you know we should, 4 factorial is really just 4 times 3 times 2 times 1 divided by 2 factorial, which is 2 times 1 times 2 factorial, 2 times 1. Okay, we can cancel these out, and we're left with 4 divided by 3 times 2 divided by 1, so that's just 12 divided by 2, which is 6. Okay, so this means the binomial is 4 choose 2. So out of 4 trials, I'm choosing 2 successes. How many possible combinations are there? There's 6. Hey, we didn't have to do all that other stuff. We could just do this formula. Yay! It's also sometimes written as 4C2, which your calculator calls NCR. So yes, we can do this on our calculator without having to type in factorials. Hooray! Okay, ladies, so here's the magic of how we can do this on the calculator. So I'm on the home screen, I'm going to press catalog, and it's not under the Flash apps this time because it's a normal probability like math thing, which we love. So I pressed alpha N, and then I got to this right here, NCR. So this is how to figure out our number of combinations. So we're going to say our original N, we had 4 trials, and comma, and then we're going to pick 2 successes out of that, and parentheses, and boom, there's our 6. No more having to do factorials the long way. Okay, so now what we're doing is we're taking what we just did, our NCR, right, which we found was 6 when we did 4C2. Right? And that's this whole big equation, and we're going to plug it into the probabilities that we did before. So our previous equation, we said the number of possible outcomes times the probability of your successes times your number of successes times the probability of the complement times your number of failures. So now we just put that all into one glorious equation. And remember that this is just my number of arrangements, or my combinations of possibilities for the arrangements for successes and failures. All right, so let's do an example. The Seed Depot advertises that 85% of its flower seeds will germinate. Suppose that the company's claim is true. Erin buys a packet with 20 flower seeds from Seed Depot and plants them in her garden. So we're going to let X equal the number of seeds that germinate, as in like turn into plants, just in case you forgot what germinate means. Question the first, does this have a binomial distribution? Okay, so to our bins, binary. Do I have success and failures? Yes, success in this case would be seed germinating, and I'm going to write this down so that we have it. So success is seed germinating, and failure would be not germinating. Seed does not germinate. So I have successes and I have failures. So we're good on binary. Are they independent? Possibly, although it's possible that one seed does not germinate. It's more likely that others will not, but we're gonna assume that it is independent. Do we have a set number? Yes, we have 20 seeds, so we have a trial number of 20. And how about the success, or the probability of success? So the probability of each seed germinating is 85%, assuming that the advertising is true. So assuming that the independence does hold, that it is true, and that they truly are independent, then we do have a binomial setting with an n that's equal to 20 and a p that's equal to 0.85. Okay, so now I want to find the probability that exactly 17 seeds germinate and show my work. So the probability that x equals 17. Okay, so I need to show my work, and by showing my work in this case, I need to actually write the equation. So I need to plug everything into the equation so that they can see that, despite the fact that a lot of this is going to be on my calculator. So I'm going to say there's 20, choose 17, okay? And what's the probability of success that they germinate? This would be 0.85, and there's a total of 17 of those, right? And then the probability of failure, if the probability of success is 0.85, then the probability of my failure is 0.15. And if there's 17 total, that means 3 are going to be failures. So if I plug this into my calculator, I get 0.2428. So if I were to list that in context, I would say that 24% of the seeds, there's a 24% chance that exactly 17 of the seeds will germinate. Okay, so for this next problem, I didn't leave a whole lot of room, so I'm going to write tiny, but if only 12 seeds actually germinate, should Erin be suspicious that the company's claim is not true? Compute the probability of x less than or equal to 12 and use this result to support your answer. So essentially, I'm going to do the probability that x is less than or equal to 12. To do this problem, I'm just going to pick, since it's less than 12, I'm going to pick 12 out of 20 because, so 20 pick 12, because if I find the probability of 12 and it's not very likely, then I know that less than that is probably not going to occur. So the chance of these seeds germinating is 12. The probability is 0.85 of 12, and then I have 0.15 is my probability of them not germinating, and there's 8 of those. So if I were to plug this into my calculator, I would end up getting 0.005921, which is an incredibly low number. In fact, that's not even, it's like 0.5, 0.6%. So I would say that if Erin only gets 12 seeds to actually germinate, then she should be very suspicious of her 85% of their flowers will germinate, because that's not very likely in this situation. Okay, ladies, so you're probably wondering, is there an easier way to do this with the calculator? And the answer is yes, of course there is. Okay, so we're going to go into the stats list editor, and we're going to go distribution, and I'm going to arrow all the way down until I get
two things that say binomial. Binomial PDF and binomial CDF. So binomial PDF is for finding a probability of x equals something very specific. Binomial CDF is for a range. X is less than or equal to a value. Since we just did a problem of x is less than or equal to 12, let's do an example with that. Okay, so I had 20 as my number of trials. My probability for success in the last given problem was 0.85. The lowest value, if I'm doing x is less than or equal to 12, then the lowest possible value is 0. And the highest possible value is 12. So I'm going to hit enter twice. And I end up with a probability of 0.005921, exactly what I got before. It's amazing! Okay, so that works. Now the question is, can I do the complement of that? What about x is greater than 13? So I can do that same thing here. So I can go back to distribution and go back to my binomial CDF and say, okay, I have number of trials, 20, probability of success is still 0.85, but now if I'm x is greater than 12, the lowest value I could have is 13, because these are discrete, and then my upper value is going to be 20. Brilliant. Okay, so I hit enter twice, and I get 0.994079, which would be the probability that this would be greater than 12. Okay, now to show you that that truly is the complement of it, let's do 1 minus the value I got, 0.994079, and I end up with 0.005921, exactly the answer that I got to begin with. So when you're using this function on your calculator, you need to make sure that you know what is less than, what is equal to, what's greater than. Okay, if it's greater than or less than, we're going to use CDF. If it's equal to exactly, we're going to use PDF. Okay, ladies, so here is what we just did typed out. So binomial PDF, n is our number of trials, p is our probability of success, and k is the value given, a probability of x equals k. So that's when we use PDF. Binomial CDF, n is our number of trials, p is our probability of success, then we have a lower upper. And this computes x, probability of x is less than or equal to k. So remembering when you have less than or equal to k, 0 is your lower and k is your upper bound. Okay, but if you have greater than or equal to k, k would be your lower and your highest value would be your upper bound. So it just kind of depends on what you're given. You can use either one. So you have to actually think about what the problem is to be able to answer this. Okay, and notice the way that this is written. The other way that you can do it is from the home screen, and you can go under catalog and then flash apps, and you can find these there as well. Just depends on what you prefer. Like I said, I always tend to prefer Stats List Editor because I'm already there. The key thing that you need to remember is you cannot just write this on the exam. They want you to use the actual real equation. So I would take the time to write the actual real equation and then calculate it on the calculator. And if you want to check it, you can do it both ways, but I mean, let's be real. Let's write it down with the equation and then check it on the calculator. So that ends our lesson today. I hope you had a fabulous snow day.